and welcome to the first part on our unit covering circuits and DC instruments. In this first part, we're going to be introducing series and parallel resistors. We're also going to introduce other fundamental concepts you need when working with circuits. We're going to begin by drawing the symbols for various circuit elements. So starting with a battery, we have a wire, two parallel lines, but one is bigger than the other, with the bigger line being the positive terminal of the battery. We have a capacitor, which looks a lot like a battery, but the lines are the same size. A resistor is a zigzag. A wire is just a straight line. A switch is a straight line with a break in it. So this switch is open and no current can flow through that particular wire. Lastly, we have a ground. There are two possible symbols you might see for a ground. I'll draw them both. Both of them look like triangles. They're just drawn slightly different. If you see this symbol in a circuit, that means that that location in the circuit is at 0 volts. Okay. So the next thing we're going to introduce is the idea of real versus ideal batteries. An ideal battery produces a voltage and has no resistance. A real battery also produces a voltage, but has a resistance associated with it. Let me make that a capital R because I made it a capital R on the other side. Okay. One way that real batteries are modeled is they're modeled as being a small resistance. This would be the internal resistance of the battery combined with an ideal battery. So this symbol here would be an ideal battery, and this combination would be a real battery. Now, because of this distinction between real versus ideal and what they're trying to show, oftentimes you will see this labeled not with a voltage or not with a V, but instead with a curly E. And it might say something like curly E equals 6 volts. Okay, that curly E stands for EMF, or electromotive force. And for all intents and purposes, for this class and this unit, you can consider that just to be a voltage, an electric potential. Next, we're going to look at what does current do at a junction. So if I draw a fairly simple circuit, battery with a couple of resistors, what happens here? Well, the battery produces a current. I'm going to call that I1. And then it hits this location. And at this location, the electrons that form that current have a choice. Do they drop down and go through this resistor, or do they continue straight and eventually pass through the other resistor? As you might expect, some of them go both directions. So I'm going to call this I2 and this one I3. And it has to be the case that I1 equals I2 plus I3. The electrons that form I1 have to go in one of the two directions. Therefore, it has to all add up. Okay. After passing through the resistors, I2 and I3 come back around and they hit the lower junction in this circuit. At this lower junction, they reform into I1. So again, that would be that I2 and I3 are coming into the junction and I1 leaves. And so that again results in the formula we wrote for the upper junction. Now you may be wondering what determines which current is bigger. And it depends on the resistance. Okay, the path with less resistance will have more current. And if the two paths have equal resistance, then the current would break equally and split in half. Okay. So now let's take this and think about series versus parallel resistors. If I have series resistors, it's a combination where they're all in a line. If you think about this as being a group of people all holding hands, your left hand is in the person next to you right, and so on and so forth. Left to right, left to right, left to right. Okay. When you have this combination, the current only has one possible route through all those resistors, and therefore the net resistance of this combination is the sum of all the individual resistances. So I've illustrated this with 3, but if I had 10, I would have to add all 10 up. On the other hand, I can hook resistors together in parallel. So I will draw that like this to the best of my ability, where this is R1, R2's in the middle, R3's on the other side. We'll give it some tails. Now if I think about it, the current has multiple paths. The electrons have 3 different choices in which way they're going to go. We will, in a later part of this unit, derive this formula, but for the moment, we're just going to go with it. The total resistance for the parallel case is found by adding inverses. Okay. Now, this formula is a little bit tricky. If you're not used to adding inverses, you gotta pay attention to what you're doing. So, I'm going to give you a little bit of parallel math, a little bit of useful math about parallel resistors. I'm also going to give you a cautionary note. So if we have 2 resistors in parallel, that's R parallel, 1 over R parallel equals 1 over R1 plus 1 over R2, which I can rewrite as R2 plus R1 all divided by R1, R2, common denominator, and that's 1 over R parallel. Now, to find R parallel, what I need to do is flip everything over. So it turns out that it is the product divided by the sum of the 2 resistances. Okay. The other thing to remember is your rules for adding resistors, adding fractions. So let's say R1 is 2 ohms and R2 is 3 ohms. Then 1 over R parallel will equal 1 over 2 ohms plus 1 over 3 ohms. And the thing that I see students do a lot is they say, 2 plus 3 is 1 over 5. And then they do other things like forget to flip it back over, and it kind of cascades from there. The problem is that 1/2 plus 1/3 does not equal 1/5. Okay, that's not how you add fractions. If I want to add fractions, I have to put them over a common denominator. So between 2 and 3, 6 is a common denominator. So 1/2 is 3/6. 1/3 is 2/6. So 1 over R parallel is 5 over 6 ohms, which means R parallel is 6/5 ohms. Okay, so please watch what you're doing. I anticipate that many of you will not use this little bit of math I gave you, but I also anticipate that many of you will get to this point and write down, instead of 1 over R parallel equals 5 over 6 ohms, you will forget to flip it and think that that's the answer. R parallel equals 5/6 ohms. So that is also wrong. Lots of wrong things there. Okay, so again, series resistors. So let's set up a basic circuit with 2 resistors in series connected to a battery. Let them be R1 and R2 again. So R series is going to equal R1 plus R2. Okay. How does the current through each resistor compare? Well, the current comes out of the battery, goes through R1, goes through R2, and back into the battery. There's only one path, so they have the same current. Okay. How does the voltage dropped across each resistor compare? So remember, as you go around a circuit, the current is not used up, but the voltage is. And since the battery is providing a voltage of V, some of it will be used by R1, some of it will be used by R2. And it will be the case that V1 is whatever that current is times R1, Ohm's law. And V2 will be whatever that current is times R2. And V will equal V1 plus V2. Okay, that's series resistors. Now let's go and think about parallel resistors. I've already discussed them a little bit, but I will draw them again. So here they are. So again, battery voltage V, R1, R2, and 1 over R parallel equals 1 over R1 plus 1 over R2. Okay. In this case, we know what happens because we've already discussed what happens at a junction. So if the battery produces a current of I, then let's let I1 go through R1 and I2 go through R2. And how does the current through each resistor compare? I'm going to say it depends on whatever R is. Right? The smaller resistor will have a bigger current. How does the voltage across each resistor compare? The voltage used by each resistor. Well, in this circuit, if I start at the battery, I come out, I go through R1, and I come back to the battery, which means that whatever the battery is producing, resistor R1 has to use it all. Okay. If I look at R2, I come out of the battery, I can go through R2 and come back to the battery, and whatever the battery is producing, R2 also has to use. So in this case, they have the same voltage. Okay. And it has to be the case that V equals I1 R1 and V equals I2 R2. And with that, I can now write that the current I1 is V divided by R1, and the current I2 is going to be V over R2. So now let's think of some common examples. So car headlights, are they in series or are they in parallel? How do you know? Well, we've all seen the cars that are driving down the road where one headlight is on, the other headlight is off. If we think about a basic series circuit versus a basic parallel circuit, in series, if this resistor or this headlight fails, then that breaks the entire circuit and no current can flow. Therefore, I can't have a car with one headlight on and one headlight off. In parallel, if this headlight fails, then this one can stay lit because it has its own path to the battery. So car headlights are definitely in parallel. Okay, on to household outlets. If I think about a standard set of household outlets, and I'm doing my best to draw, so bear with me. Toot, 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 toot. Look like little faces, right? Are these connected in series or parallel, and how do you know? Well, I know that I could plug a light into this one, and I could plug a clock into that one, and I can unplug the light, I can turn off the light, I can do whatever I want with that light, and the clock is not going to be affected. It's still going to keep time, even if it doesn't have battery backup. Therefore, these are also in parallel. Most everyday things that you encounter are in parallel for this reason. I can turn one off without affecting the other. Okay. A common example of something that is in series is old-fashioned Christmas lights. You may remember I believe it's the 12 panes of Christmas, where the guy yells that if one light bulb goes out, they all go out. That's a sign of parallel. And now you've got the mystery of, well, which one is the one that went out, going one by one through it. It's modern light bulbs. Modern Christmas lights are much better from that standpoint.